Okay, now that we have a basic understanding of circuits, we can start to think about what happens when we actually use some of the energy. And so we'll get to Joule's law, which is a measure of electric power. So the basic idea with a light bulb, I talked about this in a video or two ago, is as the current comes through here, the electrons, what we do is as it goes through a resistor, the resistor restricts the flow of electrons. And so the electrons inside of that resistor, they're banging against all these atoms. And when they bang against them, they vibrate them. And that gives these atoms thermal energy. So we move some of that kinetic energy of the electron, which the kinetic energy is actually comes from the potential energy down here. So that potential in the battery. So we have potential energy that goes into it. It bangs around, creates thermal energy. That thermal energy is released as photons in light and as heat. So we have some heat coming off there too. Let's do it in red. So it gives us heat and light and whatever we want to do with it. Other devices work the similar way, although we utilize that change into thermal energy differently. And so basically, if you remember that power is the change in energy over time. So we can define it as the change in energy or the work over time. It's work over time. Okay, so what we have here is we have a change in thermal energy would be our electric power. So that would be change in thermal if we measured it at the source, and that would be over time. But the change in thermal energy is going to be equal to the loss of electric potential. So we have that the power is going to be the negative loss in potential. And electrical potential over time. And then going back, if you remember, change in electric potential, well, that's the charge delta V. So we can substitute that in. And we get P is going to be, if we ignore the sign, then we would just have Q delta V over delta T. And then separating these two, we get power is going to be the charge, that should be a big Q, the charge over delta T times delta V, and the charge per time is what we use to define current. And so that gets us to our equation for electric power. Power is going to be current times potential difference, and the units on those are watts. And that should be familiar. So this light bulb might be 100 watts. So depending upon the current, the potential difference, I can get a current because the power is defined as 100 watts. I could tell you the current if I knew the potential going across it. We could probably do one. How about the potential in your house? So if I rearrange that, I get current is going to be power over potential difference. So the current across just a 100 watt light bulb in your house, that would be 100 watts divided by 120 volts. So you can see it's less than 1, whatever it is. Zeros, 10 out of 12, whatever that is. Anyway, but there is some relationships that we can get here. So we can link, we now have power, but we can go back because current and potential difference are in there. So we have current is potential over resistance. That's Ohm's law. And if I rearrange it, I get potential difference is IR. So we can use these and get two new ones. So power is also substituting for current, you get potential difference over R times potential difference. So power can also be defined as the potential difference squared divided by R. And if we substitute it on the other side, the power is going to be, if I do potential difference, I get I times IR. So I get power is I squared times R. And looking at these, they look very different because one you divide by R, the other one you multiply by R. And so it just kind of depends what you want to talk about. Typically, if we do over R, then we're talking about in series. They both calculate the same. And then we would do in parallel. I think I got this right. Let me check my notes. No, I got them backwards. This is parallel. This is in series. It felt wrong when I said it. Because in parallel reduces the resistance, so we get that over R. In series, it increases the resistance, so we multiply by R. But either one of these, and this is our general, this is Joule's law. Yeah, and then the last thing you may want to know is how they charge you for electricity. Because these are watts, and so when you're paying for electricity, it's based on your power usage. And they charge you by the kilowatt hour. Kilowatt hour. And that's the so that's the energy use, the potential energy use that a 1,000 watt device would use in an hour. Would use in 1 hour. So there you go. It's like 1 kilowatt hour is like 10 to the 6th joules of energy. It's a J. All right, that's it. That's Joule's law.